Here we have the translation on the t-axis. The theorem says that the Laplace transform of this one equal to e power minus as f of s, where f of s is a Laplace transform of small f of t. U here is a unit step function, so we also denoted that by u sub a of t. If t less than a, it's been sent to 0, and if t greater than or equal to a, we have 1. So when you multiply this term, u t minus a times f t minus a could be 0 times f t minus a if t is less than a, and equal to 1 times f t minus a if t is bigger than a. So the function, say f, small f of t, look like this. Then u t minus a f t minus a, what it does is will only show up when, so because everything before the times a is 0, so it will not show up until the times a. When a arrive, the signal arrives. So what it does is it's exactly the same as this shape, but with delay a times. So the new one here is u t minus a f t minus a. So it's described the signal of the same shape as that one, f, with a time delay of a. This axis is time. So now let's use this theorem, this one, to compute the inverse transform of some function. Find the inverse transform of this function. So here you see that there is existence e power 2 times minus 2s. The theorem says if we have e power minus as f of s, so our function f of s is 1 divided by s plus 3. So we first need to find what is small f of t. So to find Laplace transform of this one, we know that by the theorems we will have u t minus a f t minus a. So by the theorems, this one fits the pattern here with e minus 2s, so a equal to 2, minus a equal to 2, and big F of s, where big F of s equal to 1 over s plus 3. We need to find the Laplace transform of this one. The theorem inverse Laplace transform this one. The theorem says is equal to u t minus a. In our case, a equal to t minus 2, f t minus a, f t minus 2. So all we need to do is compute small f. Small f is the inverse transform. Small ft is the inverse transform of big F of s. So the question now becomes, what is the inverse transform of 1 over s plus 3? So this one, by the Laplace transform table, we know this is e to the minus 3t. So inverse transform of this one is unit step function a, which is ut minus 2, f t minus 2, so u t minus 2, f is e minus 3t, minus 3t minus 2. Now this is the function, the inverse Laplace of this one. And you can write down further. The unit step function is this the function ft of the same shape as this one, delay 2 units in time. So you have 0 if t is less than 0, and if t greater than equal to, you have 1 times this. So we have e minus 3t minus 3t is minus 2. So note that, as we said before, same shape as ft, e minus 3t, a time delay of 2 times delays of 2, this function. Graph it, and we graph the inverse transform this one, which means we need to graph this function, and we know that it has the same shape as ft with the time delay 2. So ft is e minus 3t, and for ft's we always consider times at least 0. So the function is here, zeros here. When t is equal to 0, f0 is e power 0, which is 1. So it's here, 1. And then because of the exponential e to the minus 3t, it would go like this. Because this number 3, minus 3 here is negative. So function ft could be something like this. Yeah. So it looks like something like this, going down to 0. Yeah. But we only start when time equals 0, so it would look like this. That one, ft looks something like this. But now for the function we need to graph, this one, it had the same shape as this one, start at the time t equal to, so it's delays here. So we just copy, we shift this graph, but instead of starting from t equals 0, we start from t equal to 2. T equal 2 here, 1 here. So we know that before time equal 2, things is just 0. Starting from time equal 2, it start acting like ft. It start acting like this. So we see it's 1 here, and then you go down, approaching 0 when t is infinity.